So it's being streamed. Start recording. All right. Welcome everybody to yet another meeting of our seminar. I am happy to present Grisha Konovalov, who will tell us about formal modular problems and their relation to Lie theory. Please, Grisha, take it away.
Thank you very much. Thanks for having me. Today, I want to talk about formal modular problems and what they have to do with differential graded Lie algebras. And that is a sort of a natural thing to talk about after we talked about cotangent complex a week ago. So let me start with the definition. So we no, just a second. Let me fix some notation. So remember last time we worked in the category of connective differential graded algebras over a field K. K was a base field. Its characteristic was 0. We worked with commutative differential graded algebras which sit in non-positive cosmological degrees, and we denoted the category of such by this symbol. And we also worked in the underlying infinity one category, which was this category with the quasi-isomorphisms inverted. And we denoted it with a fancier font. And now I also want to introduce a subcategory of Artinian algebras. So first, let me denote it just art. Art, the category of Artinian differential graded algebras over K, is a full subcategory in the category of connective differential graded algebras over K, and an algebra. Actually, it's not the same. An algebra is Artinian if and only if its total cohomology is finite dimensional. Over the base field. Yeah. And we will also use a curly fancy font to denote the category of Artinian algebras with the quasi-isomorphisms inverted. So now I'm ready to give a definition. A formal moduli problem is a functor from the category of Artinian augmented algebras. Augmented means that the unit map from K to the algebra is split in the category of algebras. Or just let me make a remark here that part augmented is actually a common category. It's the category of Artinian algebras equipped with a map to the base field. And a formal modular problem is a functor from the category of augmented Artinian algebras to spaces, which satisfies two conditions. The first one is that if we apply the functor to the base field, we shall get something contractible. And the second condition says that whenever we have a pullback diagram of Artinian algebras, such that the map from, for example, C1 to C01 is surjective on the zeros cohomology, then if we apply our functor f to this diagram, this is required to be a pullback diagram in spaces. Okay, so an example of a deformation problem, one of examples we've seen a week ago, and that was of deformations of an algebra. Let me recall that. Fix a commutative connective differential graded algebra A and define a functor of its deformations. And it sends an Artinian algebra C to the space of C algebras A prime equipped with an isomorphism of the fiber over 0 with A. So a few remarks here. First, a priori, this defines a functor with values in infinity categories. But we can check, and we will later do, that this functor in fact takes values in spaces. So what I'm saying is that a priori the right-hand side is some category of arrows in the category of cumulative algebras, and it needs to be proved that this category is in fact a groupoid. In other words, any morphism in such a category is invertible. And we will later prove that, but we will need some technique to do that. Yeah. So.
Sorry.
Yeah.
Could you recall what is the SPC?
Spaces.
Spaces is topological.
Yeah, I mean homotopy types, to be more precise. Spaces up to weak homotopy equivalences. This is an infinity one category. Okay.
Yeah, and we identify this space via the Quillen correspondence or Sullivan correspondence, or
I mean, that's not kind of level of details I want to get into. Like, I guess probably both variants are fine. Well, what we actually need is that this category, that the infinity category of spaces up to a big homotopy equivalences exists, and that's kind of suitable for constructions. Okay, thank you for the question.
Okay.
And the proposition which we want to prove now, but we'll prove it later, that def A is a formal modular space. Formal moduli problem. And you see that we kind of need to check three things. First, that def A of C is a space. Second is that this one is contractible, and this is actually obvious. And third is big condition, that it sends certain pullbacks to pullbacks. Okay, I guess we'll get back to this proposition once we learn more things about something. Okay. Let me now formulate a slogan. Maybe, no, let me just state the theorem. And I guess in more or less this form, the theorem was formulated by Jacob Lurie and John Pridham independently, but the ideas behind the theorem, they've been circling around the literature for quite a time. So I will mention Jacob Lurie and John Pridham, and I will put this sign to emphasize that, like, there were other people that were thinking about that, and probably way before Lurie and Pridham got to finally write something about it. Okay, so, and the theorem is that there is a functor big psi from Lie algebras to functors from Artinian algebras augmented to spaces. And more or less heuristically, it sends Lie algebra G to a functor which sends an Artinian algebra C to the space of Maurer-Cartan elements of G tensor with the augmentation ideal of C. And let me emphasize that this is an important algebra because an important Lie algebra because the augmentation ideal is an important commutative algebra. And image psi, the statement is that apart from the existence of such a functor, the statement is that the image is exactly the formal moduli problems.
I'm sorry, maybe this question is a bit stupid, but why MC is an important algebra? I mean, we only required some homological condition on Artinian algebras, so.
Yeah, but it's kind of similar to the classical case. Whenever you have discrete augmented algebra over a field which is finite dimensional as a vector space of that field, its augmentation ideal happens to be important for the dimension reasons.
Yeah, that's clear. My issue, I guess, is that if we replace this condition with the homological one, then maybe we can have something that is not nilpotent but homologically trivial.
Yeah, I see. But kind of that's actually the one thing that you're right about is that I probably need to actually work with local Artinian algebras, which is, yeah. Thank you for that remark. But the thing is that like we did kind of made some homological condition. That's true. But after we invert quasi-isomorphisms, it happens that this kind of category that a priori contains objects which are maybe have live in infinitely many degrees, but in reality it is equivalent to a smaller category which is actually consists of so to say important algebras. And that's one remark. But the other remark is that formula of C is mapping to the space of Maurer-Cartan elements of G tensor and C. It is a heuristic. I'm not saying that that has to be a well-defined space. So to say. But however, I will explain later how it should work in reality, I guess. And yeah, the thing is with that homological condition is that we actually can work with a smaller category which actually consists of algebras which are really finite dimensional over the base fields. And yeah, I realized that I needed to make the remark that we actually want to work not with just all Artinian algebras, but with local Artinian algebras. Let me correct it here. and C is local. I guess that's the category I want to work with. Okay, so and the statement that the image.
Sorry, and more stupid question. What does MC stand for?
Excuse me?
What is MC?
Which one? There are two MCs.
Yeah, that one.
This one is stands for the space of Maurer-Cartan elements in an algebra, in an importantly algebra.
Okay.
And this one is the augmentation ideal of the Artinian algebra C. So again, and the statement is that there is such a functor psi, and its image is exactly the subcategory, the full subcategory of formal moduli problems. So, okay, let's now we will prove the theorem, I think, like most of it, except for the last part that, let me write it down. We will prove that we will construct such a functor psi, and we will prove that the image of psi lands in the subcategory of formal moduli problems. But also we will prove that any pro-representable object is contained in the image of psi. I will later tell you what are those pro-representable functors. And this will be it. And the how to finish after we have done that, to finish the proof of the theorem is kind of make a reduction from the general case to the case of a pro-representable functor. And this is sort of a technical geometric argument which basically exploits the whereby you prove that any formal moduli problem is admits a nice cover by pro-representables. And this is a sort of a technical argument which you can look up in the Jacob's book. So I will not touch that. And now let me talk about some algebraic story, which will be one of the non-trivial inputs to the construction of psi. And this algebraic story is called causal duality. And let com be the category of co-nilpotent. I will explain what that means in a moment. Co-commutative differential graded coalgebras. And here we're working with non-conital coalgebras, and like let maybe H be such a coalgebra. And H is conipotent if and only if no, just a second. Let's make a construction first. So we define a filtration and increasing filtration on H as follows. The nth part of the filtration consists of elements of the coalgebra which are annihilated by the nth power of the cobracket. And H is set conipotent, it's called conipotent, if this filtration is exhaustive. In other words, H coincides with the union over the filtration. And just to give an example, let, I don't know, V be a differential graded vector space, complex of k vector spaces. Then we can form co-free, conipotent, co-commutative coalgebra, which I, for simplicity, just denote by co-free of V. And this is given by direct sum over n not less than 1 of symmetric, the nth symmetric power V. And it has the standard cobracket that splits a tensor word into 2 parts. And you can check that this is actually conipotent. And also what you also can check is that this happens to be co-free object in the category of co-commutative conipotent algebras. Which means that the factor of the co-free coalgebra is right adjoint to the Figurative factor to the vector spaces. And so now I want to define the Chevalier-Eilenberg function. It is a factor from the category of differential graded Lie algebras to the category of conipotent co-commutative coalgebras. And its values on an algebra G is.
I'm sorry, once more for a very stupid question, but why is it conipotent? I mean, for me, it just seems that after we apply the co-multiplication n times, we get like an n-fold product with itself of an element, and it's never 0.
Just let me give an example. Did I get it correctly that you're asking about why this co-free algebra is conipotent?
Yeah, exactly.
Oh, let me just say it to you somehow fast. Like delta restricted to V. Maybe I should write a formula for delta. Shouldn't I? Like on from this word, delta is given by the sum over, I guess k from 1 to n minus 1, and just a second, let me think. Yeah, and the summand is a splitting of the initial word into two parts. The first part consists of indices from 1 to, I guess, k. Yeah. And the other part is k plus 1 to vm. And in particular, if we restrict the delta to V, the space of code generators just gets 0, right? That's the first part of our iteration. Then, if we apply it to V or times V2, what we will get? Yeah.
It would be Vk minus 1 or?
No, if I want k to range from 1 to n minus 1, then I need let me write it differently. So I want this to be like this plus 1 times 2 times and so on. And the last summand is where we have split our word into two parts, where the first part has length and minus 1, and the second part consists of just the n. So that's what I wanted to write, I guess. Yeah.
Okay, but once again, very stupid question. Then I don't see the difference between any of the summonds.
That's yeah, I get it. So what's the target of the co-multiplication as a map? It goes for like the source is the co-algebra, and the target is the co-algebra times co-algebra.
Yeah. Okay, yeah, I see. Yeah.
So when I write that, like, when I split the word into two parts and I put those parts into brackets, like the first part in the first pair of brackets, it belongs to the left factor, and the other part belongs to the right factor. That's what I mean by that.
Yeah, I guess it was just confusing that the multiplication and the symmetric algebra is denoted by the same thing as the product. Yeah. No,
So,
I get it.
So what I was saying is that if we apply delta to the space of cogenerators to V, then we get 0, just by definition. Then let's try to apply it to the space of symmetrical words of length 2. What we will get is like the result will consist of one summand, which will live in V times V, which is a subspace in this tensor product. And like what happens next, if I apply to the result delta in one of the factors, what I will get is 0 by the previous statement, and so on. In fact, so we can you can proceed with this calculation and do it for a word of any length. So that's why the algebra is actually kind of important. Okay, so I wanted to construct the Chevalier-Eilenberg function, and it will take a Lie algebra and will send it to a co-nilpotent co-commutative coalgebra, and all of them are differential graded, of course. And the definition is that C star of G is a quasi-free quasi-co-free, should have said co-free coalgebra co-generated by G shifted to the right, shifted to the left by 1. And this is, as we just discussed, this is the symmetric quality. And it is equipped with a special differential. And I want to define the differential. And first I want to mention that because the coalgebra, the underlying graded coalgebra, is co-free, and the differential is supposed to be a co-derivation, it suffices to define the differential on the congenerators. And let me do that.
By the way, shouldn't we dualize the Lie algebra?
No, we shouldn't. I don't want that. And if you want to dualize, what you will get is a commutative algebra, not commutative.
Oh, I see. Okay, I see.
That's like the C alpha star, not C low star. And by saying on congenerators, I mean that it suffices to define a map from here to the space of congenerators. And it will consist of two parts. The first one is G1, which goes from C1 of G shifted by 1 to G2. And this is just the differential that the Lie algebra had. So this is just the differential of the Lie algebra. And the second part is sim2 of this. And the target is again G. Yeah, by the way, I forgot to put the right shift here. It should be G shifted by 2, because the differential is meant to have degree 1. So this symmetric power is actually a skew power of G shifted by 2. And the whole map is just the Lie bracket shifted by 2, which the Lie algebra G had. And this, in fact, defines as a co-derivation which squares to 0. And let me also write that all the other parts of the derivation that we are defining are set to 0. And d squares to 0. And that's a simple calculation which I want to leave as an exercise. And let me just tell you let me give you a hint, an idea, so to say. It follows from two things. The first one is that the differential of the Lie algebra squares to 0. And the second one is the Jacobi identity of the Lie bracket. Okay, so this defines as a functor, in fact, from the category of differential graded Lie algebras to the category of co-nilpotent co-commutative algebras. And it has a left adjoint, which now I'm going to define. And it is, I would like to call it co-har. Har is from Harrison. It has to do with Harrison homology and cohomology of an algebra. And this functor, it goes from co-commutative, co-nilpotent co-algebras to Lie algebras. And the definition is quite similar. So cohar of a co-algebra H is a quasi-free Lie algebra generated by H shifted by 1 to the right. And it is equipped, again, it is equipped with some differential, which will remember the co-algebra structure on the left-hand side. So, by the way, this stands for the free Lie algebra generated by H shifted by 1 to the right. And this is a fancy way to write it, where Lie of n is a is a vector space of Lie words of n arguments, and the symmetry group acts there. So, but it's not very important right now, I guess. So let's define the differential. Again, it suffices to define D on the generators. And again, the differential will consist of two parts. The first one is from the space of generators to the first part of the free Lie algebra. Which is this. This is just, and the whole thing is shifted by one. And this is just h shifted by -1. And again, this is just the differential of the algebra h. And the second part is from the space of generators to the space of Lie words of two arguments. And again, the whole thing should be shifted by 2 to the left. And this is in fact just the sim2 of h shifted by -2. Sorry, here's one, not two. So this is said to be equal to the co-multiplication of h. And the rest is said to be equal to 0. And again, an exercise. This differential squares to 0. And now let me state a few things about these functors. So the first is cohar is a left adjoint to C lowest star, and this is just as straightforward. Like, you just examine the definition, and by that you get the result. It kind of makes sense because cohar is a free, which is like it is not exactly free, it's quasi free, but it's almost free, and we know how to map out a free object. And C lowest star is a co-free, which is kind of a right adjoint. So it's not exactly co-free, but it's close to being that, and that's what makes this proposition. That makes this proposition follow from just the construction. I guess I don't want to go into details further. And the other proposition, which is not true, but I will not prove it. but I will give a reference. It's like the reference I'm familiar with is maybe not the most optimal one for this particular case. It's kind of more general, but it's a good reference. So it's book by Lurie and I don't want to misspell his name. By Lurie and right, and it's called algebraic operators. And this the exact reference is 11.3.3, and like the way you prove it is an actual computation, but in order to do the computation in more or less optimal and convenient way, you need to study those things for a certain amount of time. So like that's why I don't want to go into details of the proof of this proposition. And like the statement is the counit of this junction is a quasi-isomorphism. Okay, now let's make the following definition. So far, we have been working with one category.
Is it a quasi-isomorphism on all objects or just on cofibrant ones?
No, on all. To take any object, it's going to be a quasi-isomorphism.
Okay, great.
And like for now, we've been working with differential graded Lie algebras and co-commutative coalgebras as them forming one categories. But now we want to pass to certain localizations, and it turns out that you have to do it in a clever way. You can't just invert all the quasi-isomorphisms between coalgebras. It will give us like it will result in a tremendous loss of information. So we have to be a little bit more clever. And I want to make a definition which defines a class of weak equivalences which we want to invert in the category of co-commutative algebras. And this class is called W Kazui, and this is a class of morphisms in the category of quasi-important co-commutative algebras. And a particular morphism between coalgebras belongs to this class. If and only if we apply cohar to this morphism, it becomes a quasi-isomorphism. And now proposition. The adjunction induces an equivalence. of infinity categories. And the proof is straightforward. Let me say a few words about it. So now that we have the proposition about the fact that the k-unit is a quasi-isomorphism, the proof becomes straightforward. And so first, we need to check that both functors preserve weak equivalences. And the left adjoint does that by the definition. And the right adjoint, it does that by the proposition for this one. So let us take a quasi-isomorphism between Lie algebras. Then we can apply, just make it a bit bigger. Apply this composite to both sides. And by the proposition, the vertical arrows are quasi-isomorphisms. So is the bottom horizontal arrow. So therefore, the right adjoint also preserves weak equivalences. And so far, we have proved that there is indeed a pair of functors like this. But in order to prove that that this adjunction in fact induces an equivalence, we need to check that both unit and co-unit are weak equivalences. And this is also straightforward and follows from the proposition. Okay, so any questions about that? If no questions, let us now proceed to the construction of the functor psi. And first, let me say what we expect of that construction to be. So we want the following construction. We want the construction to work the following way. So And by the way, when I write like the alg with this fancy font, I mean that we inverted quasi-isomorphisms and get an infinity category as a result. So psi is the functor from the category of the algebras to the category of functors from Artinian augmented algebras to spaces. And it should send an algebra to the functor that sends again C to the space of Maurer-Cartan elements. And there is a way to write the space in terms of algebras, and this is just the mapping space from the dual algebra to the augmentation ideal to the Chevalier-Eilenberg construction of G. And here, I guess, I want to assume that the augmentation ideal was actually finite dimensional. And I can assume that because the category of all Artinian augmented local algebras is equivalent to the category of differential graded Artinian augmented local algebras, which are actually finite dimensional or with the quasi-isomorphisms inverted. So yeah, I guess I can do that. Okay, and but in order to make this construction work, we need to prove something. And what we need to prove is that sending an Artinian algebra to the algebra dual to the augmentation ideal is actually preserves quasi-isomorphisms. That's what we need to prove. And before we can do that, maybe, yeah. Let me first sketch the proof of this. Let me state it as a proposition. And now I want to formulate a lemma from which the proposition will follow. It is a very useful lemma whose proof, in fact, uses a lot of that tangent complex technique that we studied a week ago. And we'll get to that in a moment. But first, I want to show you how the lemma proves the proposition. And the lemma is that each Artinian algebra C is in fact is a finite iterated so-called square zero extension. And I'll tell you what that is in a moment. that means that there is a sequence of algebras, a finite sequence of algebras, and maps between them. And each of the maps fits into the pullback diagram of the following form. Pullback in the category of algebras. And this is, I'm recalling my notation from the last time. This is the trivial square zero extension. Of the base field by itself shifted by di. So this is similar to the algebra of dual numbers, but the generator of this algebra has some degree, might have a degree. In fact, it has a degree which is strictly negative by this condition, which is a thing I want to require. And let me show how the lemma implies the proposition. Okay, so that's the proposition. So let me make an observation. The functor that sends C to the dual of its augmentation ideal, it sends limits to colimits, right? Let me say finite limits to, yeah, it sends finite limits to the colimits because yeah, I'll tell you the reason in a second. Let me even maybe say that it sends pullbacks to push out, to be more precise. And the reason for that is that pullbacks in the category of commutative algebras are computed in the category of underlying complexes, provided that, like, certain pullbacks, let me say, okay, just let me be even more precise. Let me call such a diagram, I don't know, by 2 stars. And the observation is that the functor sends pullbacks of the form 2 star to push out. Yeah, and the reason for that is that the forgetful functor from the category of Artinian algebras to the category of differential graded vector spaces, it preserves those pullbacks, and it is conservative, and it preserves this particular type of pullbacks because of this condition. And it has to do with the fact that we are considering connective Artinian algebras, and the functor from the category of connective vector spaces to the category of all vector spaces does not preserve limits, but it preserves this particular type of pullbacks. And that's maybe a good exercise to think about. It should be pretty understandable. And then what we are doing is we are dualizing the result. And dualizing usually it sends limits to limits, but now we are working with dualizable objects in the category of differential graded vector spaces, because the algebras we are working with are finite dimensional. The underlying complexes are k-dualizable. Therefore, dualizing such a complex, in fact, it preserves. But okay, no, I'm sorry, it doesn't even matter, because differential graded vector spaces is a stable category, and a pullback diagram. A diagram is a pullback if and only if it is push out. So yeah, that's basically why dualizing sends such pullbacks to push outs. And the final observation that we need to do in order to make the observation work, we need to say that the push outs in the category of convoluted concommutative algebras are computed on the underlying complexes, because the forgetful functor is a left-hand joint and it is conservative. So that's kind of three pieces of the whole thing, and the whole they make up this observation. And was it understandable? Do you have questions about that? Okay, if no questions, then by the virtue of this observation, it suffices to it suffices to prove the claim for the case where C is just the algebra of dual numbers with the generator having some certain degree. And now what and yeah, sorry, I stated the proposition in the wrong way. It shouldn't preserve quasi-isomorphisms, it should preserve weak equivalences. And remember that we defined weak equivalences in the category of co-commutative algebras in a funny way. So let me write it here. Preserves weak equivalences. And now we basically need to prove that the functor preserves weak equivalences between these basic objects. And how you do that is basically you just observe what happens to this object when you apply the function. And for this, maybe let me rewrite the mapping space from this algebra to the C star as maps from, okay, basically what I need to show is C goes to MC dual goes to this goes to cohar of this preserves quasi-isomorphisms. And again, by the virtue of the observation, we just need to prove that for C being of this particular type. And it remains to note that that if we apply cohar to K shifted by minus t, equipped with the trivial co-multiplication, what we will get is just the free Lie algebra. Generated by, I guess, K minus t minus 1. And this obviously preserves quasi-isomorphisms. So I guess it proves the proposition. And do you have questions about that? Okay, if no, let us, let me think. I probably want to get back to the lemma later, but first I want to, this is an interesting statement, but, and it has to do with the theory of cotangent complex. And I hope we'll talk about it at the end of the talk, but now let me probably finish the construction of psi and like sketch the proof of the main theorem. So now psi from Lie algebras to these functions. It, by definition, it sends the Lie algebra to the functor that sends an algebra to the mapping space from its dual coalgebra to Chevalier-Eilenberg coalgebra of G. And by the proposition, this is well defined. So that's the functor of psi. And now we need to prove a few things about it. So let me state it as a proposition. first, psi preserves small limits and filtered colimits. And B, the image of psi is a subcategory in the category of formal moduli spaces, formal moduli problems. And the proof is, the proof is kind of simple. So limits. It's clear that psi preserves limits because limits in the category of functors to the category of spaces are computed level-wise, and sending LA algebra G to the mapping space from basically from cohort of the dual algebra to G itself preserves limits, obviously. And therefore psi also preserves limits. And what about filtered colimits? This is a bit more interesting. So need to prove that cohort of MC dual is compact. And again, according to the lemma, this lemma, which allows us to decompose an algebra into an Artinian algebra into a sequence of square zero extensions. Therefore, thereby writing this cohort as a finite sequence of push-outs along some simple maps between simple objects. So this kind of operation preserves compact objects. Therefore, it suffices to show that cohort of MC dual is compact for these types of simple objects. And let me write it down. Suffices by the lemma to prove that, again, cohort of K shifted by minus D is compact. But this one, this is a algebra with a trivial multiplication. Therefore, cohort is free as a Lie algebra. Moreover, it is a free Lie algebra generated by a compact vector space. Therefore, the object is compact. The free Lie algebra cohort of K shifted by minus D is compact. Therefore, we have the statement about the filtered colimits, and that was A. and B, we need to prove that this is a formal moduli problem. So there were two conditions, if you remember. So first, we need to show that its values on the base field is a contractible space. And this is obvious because this is going to be the functor sends k to the mapping space from the trivial, not just trivial, by from the theorem's coalgebra to some coalgebra, some other coalgebra, and because 0 is an initial object in the category of coalgebras, the space is contractible. And the second condition was about preserving certain pullbacks. And let us consider one of those pullbacks. And one of these maps is required to be a surjection on H0. And this is a pullback diagram in Artinian augmented algebras, which is a subcategory of connective. But let me call this condition as let me denote the condition by 3 star. But it follows from that it is in fact a pullback in a bigger category of non-connective algebras. And this is not automatic because the functor which embeds connective subcategory into the whole category does not have to preserve limits. And in this case, it doesn't preserve limits. But this particular condition implies that we can compute the limit either in the connective category or in the whole category, and the result's going to be the same. And now from this, it follows that the diagram of dual algebras is going to be pushed out. So, and mapping out of a push out square gives us the pullback square, which is what we were aiming for, 8, which we were aiming at. So that's, I guess, the end of the proof of the proposition. So now let me also, it's 5 minutes left, I think. So I will not, obviously, I won't be able to tell you what, all of what I wanted to tell you, but nevertheless, I'll try to be informative in the last 5 minutes. And maybe one proposition is that psi contains representable objects. And it also contains its filtered coordinates, which are like co-representable objects. Or not pro-representable objects, they call it. Yeah, I guess. And probably these are called co-representable. And the proof is simple. So, for example, let us fix B in Artinian algebra, Artinian augmented algebra. So we want to prove that C mapping into functors from B to C is in the image of psi. Okay, so this got to be more or less formal at this stage. And I guess because the algebras are Artinian, we can dualize them. And this is going to be an equivalence. Yeah. And that coalgebra MB dual is equivalent to the Chevalier-Eilenberg coalgebra of Kohar applied to the MB dual. So the functor which is co-representable by B, which we can call spec B. This is spec B. Spec B is equal to psi of, is isomorphic to psi of Kohar of B dual, which lies in the image. And we can also check, and this is formal, that M of psi is closed on the filtered columns. Which gives us the result for the pro-representable objects. And maybe I don't have time to prove that, but maybe stated as a statement without proof that def A, the deformation problem which we studied at the beginning of the talk, is actually isomorphic to psi of we need to take the tangent complex of A, which is dual to the cotangent. And it turns out that there is a Lie bracket on this thing, and some natural Lie bracket on the global sections of the tangent complex. And this Lie bracket gives us exactly the functor of deformations of A. So that's, I guess, if you know how to prove the lemma about the sequence of square zero extensions, you will probably be able to prove that as well. At least you will be able to prove that the def A is indeed, in fact, a formal moduli problem, and therefore there is a Lie algebra. And you also should be able to prove that the underlying complex of that Lie algebra is given by the global sections of the tangent complex. And maybe quickly, final last remark. Like I can do that. I can do the same thing for a scheme. Probably derived. And I can define the deformation factor of the scheme, which will also be a formal moduli problem. And an interesting fact is, which I wanted to state, is that def of X is pro-representable, which is the same as a filtered column of representables. Just to give an example of a pro-representable factor, which kind of naturally occurs in filtered limit of representables. If H0 of the tangent complex of X is trivial. So that's, I guess I should stop, and I'll stop there. Thank you very much for listening. Do you have questions?
Okay, if there are no questions, let's thank the speaker for this wonderful talk. And yeah, let me stop the recording here.